All right, lovely. I checked this morning and realized that I actually forgot to write the abstract. So hopefully I will deliver on what was there, which was granted very sparse. But we'll talk about path coverage in GCC. So this is me, this is my company, and this is what I do. I write patches. So path coverage, this is the next step in structural coverage. I'm going to talk a little bit about that. And I would argue it's the next generation of structural coverage. It's a new feature. We're aiming for GCC 15, which is probably going to be released in May next year. So hopefully we'll be in there. And for this talk, I did a little bit of digging in the lineage of coverage support in GCC. In GCC 3.4, released in 1997, we got branch coverage, statement coverage, and then in 2024, GCC 14 got MCDC support. And then hopefully now in 2025, in GCC 15, we'll have path coverage. This is what funding does to a project. This is driven by the needs of spaceflight. It's currently NASA that are funding this for their needs. It turns out software has to be pretty correct if you want to run it in space. And hopefully the flights won't crash. And I will be able to watch that and be a little bit part of it, which is pretty neat. So let's do a quick summary over structural coverage. I need to stop using the spacebar. Structural coverage. It's probably even more familiar if you do the examples. You have your statement and line coverage, which is pretty obvious. Have you executed every statement? You say line coverage colloquially, but it's kind of poor because you can have more statements per line. And you can have statements that span lines. So statement is the correct one. You have your branch coverage, which is sometimes called decision coverage. And then you have condition coverage, which is then sometimes called branch coverage, depending on your perspective. And finally, you have the most mysterious one, I would say, the modified condition decision coverage. It's a bit of a mouthful, so from now on, I will say MCDC for that. The rundown has every statement in the program been executed. If a statement hasn't been executed, you haven't tested it, obviously. Decision coverage has every decision in the program been made at least once during testing. This corresponds roughly true or false to that question means did you take the then and the else? Like has both the then and else of a branch been taken? Then you have condition coverage where you ask the question, has every condition that is Boolean variable that you are evaluating been seen as both true and false? This is called branch coverage sometimes because if you look at this from a graph perspective, these are all branches in the graph. That's where the mix-up happens. An example of that is the expression A and B and C, right? So in this case, you have to evaluate C to true and false. And by extension, in order to even evaluate it in the short-circuiting semantics, you need to evaluate A and B to true. And then finally, well, I mean, we've all done that, right? The odd one here is modified condition decision coverage, which states that, or which asks the question, has every condition taken on both true and false while having independent decisive power over the outcome? If you want to learn all about it or more about MCDC, I did a talk on it 2 years ago, last year maybe. There's a bit of material out there, a few papers. But the gist of it is this. So in this case, we are evaluating A and B to true and C to false. And the question is, A and B, do they have any decisive power over the outcome? And the answer is no, they're dominated by C. Because if you flip either of A and B to false, the outcome is still false. So that's what we're testing there. Now what's interesting is all of these metrics so far are what I would call block-oriented. Okay? I'm going to expand on that now because I made up this term and I have no idea if it's ever going to catch on. But it's very they're limited in scope. They're focused on very much individual units. And we compose our programs of these individual units, and it's very important to ensure that they're tested and covered. You have your individual statements, your individual decisions, and your individual conditions, expanded to MCDC, conditions of individual decisions. Data flow. Data flows through the program. Data is a river. This is really the art of analysis on data dependence. We want to understand how our program interacts depending on the data that we're pushing through it. Breaking it down a little bit, data dependence tries to answer a question like, when a variable is used here, where does it come from? Is it used? Is it initialized? This is obviously a common problem in C and C++. What is affected when I write to a variable? Right? Those are the questions that we want to answer when we talk about data flow. Data flow analysis is a huge, huge bit about static and dynamic analysis. And MCDC in particular, unlike the other criteria, is a data flow problem, because the interaction of data will actually cancel out what would otherwise be an observable effect. This bleeds into coverage, right? It bleeds into coverage through things like the definition use pairs. This is the definition I found online. I don't remember if it was Wikipedia or not, but it probably was. It's the associations of definitions and uses capture the flow of information through the program. Okay. I cannot follow that at all. But if you break it down a bit, it gets a little bit clearer. Definitions occur when variables are declared, initialized, assigned, or received as parameters. It's when you say a variable is defined. This has a sort of temporal component. Definitions are used when they appear in expressions, conditional statements, returns, or passed as parameters. That's when you consider using them. So here's an example program. This is it's a binary search. We're going to spend a little bit of time with this program because it's going to appear later in the presentation. But we define our min and max. There's even a bug in the slide. Look at that. It says use min on the second line, which is not supposed to. I'm sorry, it should just define max. But when it calculates the mid, it defines the mid, and it uses the min and max to do it. So that's an example of definition use pair. Likewise, in the check for the while loop, you will use both a, mid, x, min, and max. And you can see how this goes, right? So definition use or definition use pair coverage requires you to ensure that every pair of definition uses are executed. And going back to this example, when you define max at n, you're using it in the calculation of mid, and which also defines max, which is used in the top of the while loop. It's also used inside the while loop, and then redefined again in else. So you need to test that both the max is used in the top of the while loop, in the mid calculation there, and then likewise when you go through the loop from the max. And all kinds of pairs. This grows very fast. the thing is, definition use it's kind of awkward, but it has the power to detect longer range effects, because we're now not focused on single blocks, but we're focused on the relationship between data when it's read and when it's written. John Reger, he was here last year actually. He created this example on his blog. So John lives in the desert and breaks compilers for a living. If there was ever a more perfect job description, I would like to know. So this is a bit silly because it's 4 lines long, right? But in this case, you have a pointer and you can just assume that x here is just a global integer. And if you take the a larger than 10, it will be set to null. And if you take the, at the same time a is less than 20, you will return the dereference pointer, which is obviously undefined behavior, right? Because you're dereferencing a null pointer. It's very bad. If a is larger than less than 10, or what is it? Comparisons are difficult. Anyway, you need to take both of these thens for this to be a problem. But it's perfectly possible to achieve line, statement, and condition coverage for this without actually triggering the bug in your tests. Now, definition use would catch that. And you think, I mean, obviously, that's the thing, right? Everyone's going to catch that. How about now? I added some line numbers. If there's some 110 lines in between the definition of this and the use, would you now detect it, right? Problem with slideware is that it's all artificial, right? Definition use would detect this because you're defining p in line 3 and you're using it in line 120, and you have to test that pair in order to satisfy definition use. Let's talk about graphs. We represent the structure of a program as a graph. I'm stating that as a fact. That's what compilers do, but all kinds of tooling do this, and it's really how we think about it most of the time. And the graph is actually a very powerful abstraction for structural analysis. Very, very powerful. In this graph, we have our nodes. They're called basic blocks. I might use these terms interchangeably. And a basic block is just an uninterruptible stream of instructions. It's really what it is. So if you enter the basic block, you are going to execute all of those instructions, until you reach the end of the basic block, at which point there will be a decision on what to do next. And your edges represent the control, the transfer of control between basic blocks. This is all a bit much, but a cartoon goes a long way. So here's the same program represented with basic blocks with edges in between them. And here you can see a very good example of why condition coverage and branch coverage are sometimes conflated, because the second and third block from the top is the loop condition broken into 2, right? One per decision, or 1 per condition rather. This is how the compiler breaks down your program. And this is where the analysis happens, in a structure like this. Okay, we're going to simplify this cartoon by just giving them numbers. And hopefully, if you can't tell, then please trust me. These are the same, except I replaced the code contents with numbers. Right, now that we're all compiler engineers, path coverage is different from these block-oriented metrics because this works at a function level. Definition use works at a function level, right? We're no longer concerned with sort of addressable units. We're concerned with data flow through this, which is at a much larger unit. So let's look at an example. If you have a program where you have 2 sequential decisions, if x, then something else something, if y, something else something else. if you represent this as a graph, it looks like this. Okay? Through this program, we have 4 paths. You have the first path where you take both thens. The second path, you take the first then and the second else. The third path is the first else and the second then. And finally, you have both elses. Some more computer science. A walk is a sequence of edges which joins a sequence of vertices. Okay? Hopefully this is all familiar from uni. Whereas a path is a sequence of edges in which joins a sequence of vertices in which all of the vertices are distinct. I just realized now I used node earlier and vertex and vertices now. They're synonyms. Mean the same thing. So okay. A path is a sequence of edges which joins a sequence of nodes in which all nodes are distinct. The goal of path coverage is to ensure that your test suite executes every path there is in the program, which gives us 2 immediate problems. It gives us the problem of loops, and it gives us the problem of path explosion, and we'll explore both of those. So the problem with loops is that n iterations is different from n plus 1, right? So 10 iterations is a different path than 11 iterations, and this has the unfortunate property of going to infinity. It's a pretty big space to cover. In this space, there have been different strategies for different areas. So in the 1970s, the goal was to execute all of the loops at least once. In the 80s, we talked about exactly once. In the 90s, we're at more than once. And finally, in the 2000s, which is approaching on some 10, 20 years, we're talking about prime paths. The other problem is the path explosion. Problem is that even very small graphs can have a very, very large number of paths. So we want to tune our definition a bit to overcome these practical limitations. One is we want to introduce a simple path, which is a path where all of the nodes are distinct except for possibly the first and the last. The first and the last thing helps us with loops. That means you can execute the full loop. And that gives us a useful definition of simple path coverage. Has every simple path in the program been taken at least once? That's what we want to figure out. Going back to this if, double if program, this program has 41 simple paths. You might want to double check that, but I have twice and I might still get it wrong, but it's bad. Simple paths grows very fast because path 1, 2 is distinct from 1, 2, 3. And 1, 2, 3, 5 is distinct from 1, 2, 3. So this grows, absurdly fast. One thing you can notice here is that in order to take 1, 2, and 3 in sequence, can already do 1 and 2. So there's not really a need to track it. So what we do is this. We pick out, in this case, 4 paths. And by taking these paths, so 1, 2, 3, 5, 6, 8, 1, 2, 3, 5, 6, 8 is all left-leaning branches. We sort of cover everything by doing. So remember with the bold where you had 4 sets of paths that you could take through because you can take both thens, both elses, and either or in either direction. In either order, which sums up to 4. So we really have 4 interesting paths there and 37 not so interesting paths. which gives us a good definition of the prime path, which is a simple path that is not a subpath of any other simple path for the same graph. Okay, prime paths and loops. So loops must be taken, skipped, and exited. That's our goal. And what this goal gives us is it gives us pretty decent coverage over the behavior of loops, while at the same time keeping the number or keeping the growth of paths somewhat in check. So let's go back to our binary search, because it actually has a loop, unlike the double if. Now, this graph has 20 prime paths, which is less than infinite if we would do all the loops n+1. And these are all of them. Notice especially the ones that start with 4, which is by the middle of the list there. So 4, 5, 7, 2, 3, 4, 4, 5, 7, 2, 3, 8. Is an example of both taking the loop and coming back to the loop header. In the other case, it's taking the loop and going to the exit of the function. You have, was it 4, 6, 2, 3, 4, which is taking the loop but taking the other decision in it. So this is an example path where you go from the top of the function directly to the exit and you skip the loop. Obviously that has to be covered under this, because you really have 4 interesting variations here. This is the case where you start at the top and you go through the loop. What happens after 7, we don't care for this path, because in practice this is probably going to loop a bazillion more times, right? But we now have the path that goes from the top all the way to the end of the loop, and then it would now start repeating. So this is entering the loop. We have this case where we start in the middle of the loop, counting. We take the loop and we re-enter the loop. So you're going around the loop, and finally, somewhere where you exit the loop. Right? So we now have the case where we skip the loop, we enter the loop, we exit the loop, and we exit the program from the loop. So prime path coverage strikes a pretty good balance between the quality of the coverage in terms of what defects you can expect to find, the growth and the number of tests, and loop behavior. So what we have is a little bit of a demo, and live demos are great because they never work. I have to find my shell. Okay, it's there. There we go. There we do not go. Where is it? Oh, okay. My apologies. There we go. Make this a bit bigger. So I have a program here, which you might recognize. So I've had to clean this up a bit in order to make it actually run, because the slide one don't. I've also mixed it up a bit by adding a ternary at the end, because we need to return, right? And then what I have is a very nice haystack of, well, anyone recognize it? Yeah, it's the Fibonacci, except I had to skip the first one because I don't want repeated numbers in my sorted sequence for the binary search. And then a main that just does it. So what we're going to do is we're going to compile it. And this is a development build of GCC 15. So this is not yet available unless you pull some patches from a mailing list. you pass it coverage and the new flag fpath coverage, and it builds. And what this will produce is this GCNO file, which is a notes, which is gcov's format for describing the program. And then we're going to run it. And I forgot to make a note of the input we're going to give it. So there we go. So we take our gcov and give it a new flag prime. Let's do standard out always. I cannot type. Prime path. This was much harder than I expected it to be. Okay. And just give it BS. Okay. Can I make it a bit smaller? How is it to read back there? Jason? It's okay? Is this okay still? Okay. Well, and here we're actually getting a report. Prime paths. We're getting a report on the number of paths, 0 out of 24. So we got another 4 paths because of the ternary. This is why it differs from what was on the slide. And on top of that, gcov here actually tells us what is missing. I might actually have an old build here. Pardon? Yeah, I haven't run the program yet. No, I have not run the program yet. So this is what we're getting, 0 out of 24, right? Since GCC 14, I think it'll be made for 14, we can exclude main because we don't care about main. And only get the BS one. Just makes it a little bit neater. Okay. We run it and we search for 5. And we get 3 because it's at position 3, which is not the, it's the 4th Fibonacci number, but we're gonna be 1 off here, as is tradition in computer science. And if we run it again, let's do head actually. The number of paths covered has changed from 0 to 12. So here's the thing, even though there are a bazillion paths, a lot of them will overlap in actual execution. So you don't necessarily need 24 test cases to have full path coverage for this. Okay. Let's run it again and not find the element that we care about. So we run it with 6. Should be not found. Lovely. 13 out of 24. So that test case gave us 1 more path. But it gave us 1 more path, so we're very happy about that. Prime path. Sorry, I'm going to use path and prime path interchangeably here. Thank you. It's prime path. All right. So if you ask this about branches, you can tell that all of the branches in this program have been taken at least once. But we're still nowhere near of achieving path coverage. So obviously this is much stronger, right? To answer that point, the branches it reports here are only for the branches in this while loop, which is just an example of how sort of block local this is, or statement local this is, expression local. But path coverage works at a function level, so it has to be reported at a function level. Now, that report was pretty dense, and we want to report for humans and, you know, occasionally machines. So I thought of something that when I figured it out, it felt so obvious and inevitable that it has to be, which is this format here. If you give it prime path source, you will get a bunch of these paths that you haven't covered, and it will list you the lines that you have in the order you need to execute them in order to cover that path. So in this case, path 0, we need to cover a path from the start of the function where the middle element is not the one we're looking for, and the minimal or the lower element, the lower range of this input that we're searching is still less than the maximum. And finally, while the x is larger than the element we're looking for. Okay. The needle must be shown to be larger than the middle element on the first iteration, is what that path translates to. And here G-code actually tells us, it tells us exactly that. So we figure it out. Okay, let's try it. Well, that would cover it. Can even confirm by doing here prime paths source. And here's the, let's make head a little bit bigger, shall we? Right? Path 0, true, true, true. So, and this is the decision you need to make at every condition in order to do the path. So we run BS with 700, not found. And now path 0 is covered, and we're up at path 2 as the first one we haven't covered. Lovely. At this point, it lists, this is a quick way of just listing all of the paths you have yet to cover. This is quite a big bunch. So let's do an experiment. Let's do a for loop. Does that look okay? Let's give it a go. So there's a lot of elements you can't find, which is maybe unsurprising. In this case, let's give it to less. So we gave it the input 0 through 5,000, which should both hit and miss every element in the list on either side. And there are 16 out of 24 paths we still haven't covered. Okay, what's going on? So let's look at this program for a bit. Oh, there we go. Let's look at this path. Okay, so in this case, we need to start from the top, not find the first element in the middle, where at the same time we have to fail the check where we're still in range, and at the same time find the element. So really what we're asking here is we want both of these to be true at the same time. We want both the middle element to be x and the middle element to not be x at the same time. I think that's going to be very difficult. Okay. So let's, before we move on, let's look at some reports from machines and maybe some humans. Some humans. This is the one you saw, the lines one. This reports the exact same information as the one that printed the source. But this one is better for machines because it's line oriented. So what it does here is it prints out the lines, the last line of the block that you need to run in order to cover that path, and it includes the decision you need to make. This is much denser, and it's useful when you're iterating on this because you can grep and you can just sort of pay attention to how that set moves because it's denser, so you have a neater working set. This is not so great for figuring out what the path is and how it behaves and trying to understand the relationship that you have in your program, but it's very useful regardless. Here's a comparison of the two outputs. So this is for the same path. You can tell it's path 2 not covered. You list the decisions on lines 9 and 17 as true, true, and false, and you can tell it's true, true, and false on 9, 9, and 17. So it's all the same information, it's just in a much more denser format, which is useful when you want to monitor it with machines. Let's talk about subsumption. So who here has not programmed C++? No hands. Lovely. All of you know what subsumption means, right? Because it's in the standard, which you have read. To subsume means to include something or someone as a part of a larger group. I looked that up in the Cambridge English Dictionary, which is an authority on C++. And what that means for coverage is that a coverage criterion 1 will subsume the coverage criterion 2 if satisfying 1 also guarantees satisfying 2, right? Because the question on some of this is, why care? Well, condition coverage implies decision coverage. If you have guaranteed or is shown that every input to a Boolean function has been taken or evaluated, then obviously you have evaluated both outcomes, unless it's a tautology, in which case you've proven that it's a tautology. Likewise, condition coverage implies statement coverage, because the only way you could not cover a statement is if you're not taking the branch that statement is a part of, and by covering all of the conditions, you cover all the decisions, and by extension, all the statements. And here's the kicker. Who by now remembers definition use? 1. Maybe 2? Maybe 2. Definition use catches, it's a data flow analysis that catches just a remarkable set of bugs. It's very effective at that over long ranges because it has to track these pairs, right? But I cannot for the life of me remember it, and analyzing it by hand is just miserable, and tools don't really do that very well. But prime path coverage has been shown to subsume statement coverage, branch coverage, condition coverage, round-trip coverage, and definition use. Now what that gives you is a much simpler metric, because we can all relate to paths to our program. It gives us a very simple metric that at the same time you can throw away the measurement of all of these things because they're sort of implied by the time you get to the condition coverage. The prime path coverage. On top of that, it is very sensitive to dependent conditionals and infeasible paths. And both of those, and especially in the context of safety critical systems, knowing about dependent conditions, knowing about infeasible paths is incredibly important to make statements on the operation of your software. Combined with MCDC, you now have a very strong set of metrics that are pretty easy to understand. Maybe MCDC less so than prime path coverage, sort of for free, right? And the good thing is it's still simple to reason about. So let's talk about effective coverage. Because I've done all of this talk sort of under the assumption that you care about coverage in the first place, which I know can be a bit of a mixed bag. The most important tests you do are derived directly from your functional requirements. Like, what does this software need to do? Have you verified that it does what it needs to do in the circumstances it needs to do it? These are tests that are derived from properties. They could be hand-rolled, driven by stories, bug reports, fuzzing, bunch of sources. And the thing is, coverage on its own is pretty worthless, but it does complement testing. So this is a strategy for evaluating how well your functional test suite, how your testing processes map onto your requirements and onto the behaviors that you want. So coverage is kind of about understanding the tests, right? You're not writing a test to satisfy coverage. You're using coverage to figure out what what functions aren't properly tested. I would actually go a bit of a limb and say what you're really doing is you're trying to understand the spec, right? Because if you have functional tests, it's reasonable to assume that you have pretty good coverage, because either way, if you don't, you have either a bug in your test, in your program, or in your spec. Now, remember that the first 90% of the testing accounts for about 90% of the bugs, and the remaining 90% of the testing will account for the other 90%. There are some practical limitations to this still. There is a problem we can't get away from, which is the path explosion. The problem is that the number of paths grows exponentially with the complexity of your program. So what this does do is it forces you into a specific style of programming if you want to satisfy prime path coverage. That's kind of okay in a way, because your goal here is to have code that is easy to reason about and easy to reason the functionality about, and maybe this sort of goes a long way for that. Heuristics will control when the instrumentation gives up. The goal with that is we need to avoid ballooning compile times and object sizes. And I have an example of that in an old school C program called tree, which is an alternative to ls sometimes to dump the names in directories. You might have used it. So if you check out Unix tree 2.15 or whatever the latest version is, 2.06, 2.05 maybe, you will find the tree.c program has 1,429 lines over 31 functions. And then if you build it with coverage enabled, it takes on my machine about, well, slightly less than 200 milliseconds and produces, and this is with just branch coverage, and produces a 104K executable. If you run it with path coverage, it takes just over half a second, so roughly 3x, a little bit more, and produces a 264K object. Take. When you compile this with an effectively infinite limit to the number of paths before instrumentation gives up, the picture is a bit different. It looks like this. It will compile for 2 minutes and 26 seconds, produce an object file of 32 megabytes, and when you strip it, you're down at 28 megabytes. This is the little source file that could. 2 functions account for all of that. There are about 1 million paths each. So this whole process in GCC is built on computer science. Sometimes I hear engineers say that computer science doesn't matter. It does. I implemented an algorithm, most of an algorithm, described by a few fellows called Fazli and Afsarshi. I'm probably not pronouncing that right, but my Farsi is pretty terrible. Which is described in a paper called a time and space efficient compositional method for prime and test path generation. So in there, what we do is we compute the component graph of the CFG, of the control flow graph that we saw earlier. We find the prime paths in the components, and we find the prime paths of the component graph by brute forcing. And then we do some clever merging of those. So remember subsumption. Subsumption is a nice word because it can also apply to this idea of subpaths that aren't to be included because they aren't prime, right? What we need, well, actually, so before we get to that, we use a very compact set representation. So what's nice about paths is that paths are essentially strings where the alphabet is drawn from node IDs that you can just distribute over the blocks. By lexicographically ordering that, you can use the path index, which is what you're actually seeing in the G-curve, as an index in a large bit set, which we use to very quickly record paths, both as we're going and when we have them covered. To eliminate subpaths, my goodness, to eliminate subpaths, we use a suffix tree. I haven't seen that described by anyone that tries to tackle the problem of prime path generation. Honestly, this is a pretty brilliant idea because the suffix tree naturally has all of the properties where it will eliminate sameness in an effective way. So I use a OK algorithm, which is square. I think that can be improved upon, but this also gives me a very compact implementation, which turns out to be very fast in practice, because I can store shared paths very densely. So I only need to store where paths deviate. And finally, when we do there is some optimization where we try and reduce the amount of instructions we emit by doing some folding and redundant code elimination. That too turned out to be a pretty interesting problem. So go try it out. Go cover some paths. This is how the sausage is made. Would you like to see how to improve the binary search to improve path coverage? Yes, lovely. I'd be very embarrassing if you said no. I don't know why I gave you the choice. There we go. Okay, so the problem here is that if you look at this, might even go. So actually, the implementation of the binary search I stole from some Swedish guy's lecture notes. And what's great about that is that the implementation is terrible, because binary search is hard. And what you will notice here is that you have all of these interdependencies between data that gives you literally 10, 15 paths that you can't cover because you have your mutual exclusion. You have these contradictions that you saw, right? Was that the slide after? No, it wasn't. So here, for example, too, you're using the mid, which you're kind of deciding upon in the loop header, and then you're computing mid again, and it's just a lot of dependencies. And what's nice is that if you saw from the report, after running literally every input that makes sense, you're running 5,000 inputs, 5,000 integers that you're searching for here, you're still left with, what is that, 8 paths that you literally cannot cover, right? So you have 8 paths that are just dead. And just eliminating them and making sort of the qualified decision, is this a problem, yes or no? And obviously this program is borderline trivial. And I say it's trivial, but it's super bad. And actually the lecture notes had a bug, it used the wrong comparison. You can now actually make a qualified decision, is this a problem or not? All you need to do to fix this, because I mentioned this kind of forces you into a specific style, is BS2. All right, there we go. Do you see the difference? So I moved the computation of mid into the loop, and I don't compare to did we already find the element in the top of the loop. I push that down into the body, which doesn't reduce the number of comparisons we have at all. And then I immediately return the index of the element if we found it. And only when falling through, you return the -1. That's it, right? I would say that this is much better and much easier to understand, because you now don't have to deal with 2 things in the loop. It's just better, right? Yeah, which is terrible rule. Right, so, but yeah, so he points out that there are coding standards where this is not permitted because you have multiple returns. My not so humble opinion, throw those manuals in the garbage. Right, this is why you want multiple returns. One of the reasons why. So let's build it. Let's do coverage, fpath coverage, bs2. .cobs2. And to save ourselves some time, we're going to do the for loop again, just immediately, and do bs2. So semantically, these programs are supposed to be the same, right? They find all the same values, they operate the same, they're equivalent for pretty much all intents and purposes. But if you now look for the coverage on that, so let's do less, there we go, bs2, there is only one path that we haven't covered. And we also removed some paths because we got rid of the stupid ternary. And which one is that? The only path we haven't covered is the one where our search range starts at being empty, which ideally is an impossible path, but it's user controlled, so there has to be a check for that. Thank you. I think we have some time for questions. 10 minutes. Yes. If you can remove the...
Yeah, if you can remove the possible paths, you can actually prove that they are not reachable.
Possibly. It should be possible. If anything, this is a pretty good hint, but this has to be input driven. And some paths are only impossible, because I mean, this path exists in the graph, but is only made impossible by data, right? So if you want to test that your precondition checks at the top of a function, for example, work properly, running it through this is a pretty good way of empirically showing that it's okay. You might be able to remove some impossible paths programmatically. GCC will definitely do it in some cases under optimization. So I suppose, yes, there might be. Some of them you can't know because you don't know if the range of inputs have been verified. Yes?
So this might be an unfair question, but the hardest problem I deal with is how do you do MCDC in the const-expert code?
So the hardest problem he deals with, how do you MCDC in const-expert code? I've had that fight for a year. My opinion is you don't, because this should be concerned with what you do with runtime. MCDC is a data flow problem, and you can verify what happens in the const-expert by looking at the compiled output. Unless the const-expert turns out to be actual runtime code, in which case you already got it. So the extension that is, but const-expert is a different type of runtime. Sure, but your compiled program won't ever exhibit the behavior that you discarded during your compile time computation. And especially the way this is, by the way, in the context, or derived from the context of the automotive, in which case what you are concerned about is the runtime behavior. So, but there has been a debate for that forever, and I've so far been unconvinced that the compile time argument holds, because what you're concerned about is failure at runtime.
It's just very weird because you have 100,000 lines of code, and then you say we have 3 test cases and 100% test coverage, and no one believes you.
Sure. Yeah, but I mean, you can prove that. So there are then cases with 100,000 lines of code and 3 test cases that has 100% coverage, how is that possible? And with const-expert, it certainly might be. But then you've shown that these are the paths that the program might actually do at runtime.
Okay, yeah, that's an answer.
Okay.
Does it work with exceptions?
Does this work with exceptions? Yes, it does. It works with exceptions, and you see this false here? If this is an exceptional edge, it will throw. It will show throw. I don't do C++ for these demos because it's complicated. So what I am less sure about is what happens when you do exceptions that are handled in a parent function without or in the parent scope with unwinding. If the paths you've seen are properly committed, I think they are because we commit as soon as we can, but there is a risk of I don't think there is, but there might be a risk of a function in the middle of a basic block, a call, that will then throw in the middle of the block, but then be unwound. Sorry, do you need to change?
Every call for function which can throw, or operator, or any which can throw, must be in new region or block.
Yeah, in a new block. And I think I think GCC already does that everything that has some throwing behavior will be in its own block. In which case they should do just fine, because we flush everything on the entrance to a block before the call happens. So it should work. I've never seen a case where it doesn't work, but we give it to the world and have them break it. Okay. Yes.
I'm not very familiar with coverage and all of this cool stuff, so I'm just wondering if it's exclusive to GCC or does Line have some similar things or other compilers as well?
So the question is this exclusive to GCC with coverage? No. So LLVM has coverage, but it does it on Clang, it does it on the source level, whereas this is at the object level. Clang has MCDC with a slightly different flavor, starting from 18. Path coverage, as far as I'm aware, is a GCC exclusive feature currently. But here's my number if you want it in Clang. Jason, yes. So is there a known effort to use this information to generate fuzzing test cases or other novel inputs, right? Not as far as I'm aware, but this is new and not merged yet. This is perfect, by the way, in combination with fuzzing because it allows you to actually explore and show what fuzzing has covered or not, right? So it could be a good hint for what to throw it at.
There are fuzzing tools that are driven by some sort of path coverage.
Yeah, so the other aspect is that the fuzzing instrumentation already does some of this internally as a way to drive it. And you can derive a lot of paths by inspecting jumps in the instructions, so you can use that one too, in theory. But I don't know to what extent they do it. But sure, this is a perfect match with fuzzing, property testing, all kinds of randomization stuff. And especially if you want to show if something is actually an infeasible path, if you can take the path or not. Because if you run a fuzzer for 15 hours on this and you still haven't taken a path, it's a pretty good chance there is a contradiction in there somewhere and you're actually guarding properly.
So really dumb question. The path coverage subsumes the MCDC or no?
So the question is, does prime path coverage subsume MCDC? No, it does not. So you need both. But together, they're a superpower because it subsumes all of the other ones, including very powerful ones like
So the
definition use.
recommendation is to use both.
Right. Unfortunately, if you need to use both, you can do... Oh my goodness. Turns out... Yeah, if I was only able to type, luckily that's not what I'm being paid for. Condition coverage. Oh, there you go. So that's MCDC.
Okay.
But no, it does not subsume MCDC. You need both. There's, you can do a pretty simple example with, this comes back to path coverage, unlike definition use, which is a data flow problem, is actually a structural analysis on its own. It just happens to also subsume definition use. So you can actually throw away the data analysis because you do it structurally, which is quite neat. MCDC is a pure data flow problem because you have this cancelling effect.
So here, we're running out of time, but say I'm shipping with Clang, and I run this on GCC. Are those results valid because it's object level, and I analyze the actual object that I'm shipping?
Yeah, that is not a dumb question. So the question is, if you're shipping with Clang, and you're doing this test on GCC, are the observations valid? It's complicated. The short answer is no. This is at object level, and the GCC might change the layout of the control flow graph between versions, especially optimization flags throw a wrench right in this. The thing is, every transformation the compiler is permitted to do has to preserve semantics. So even if this is done at debug and then no optimization, if you trust that optimization will not change semantics, you're well covered even with the object one. And then whether or not you want to trust that is a different discussion, but no, so they're not compatible. Still though, this does capture the semantics of flow. So the exact paths might change, but the relationships between your data and your structural blocks, they really don't change that much because they're driven by the semantics of the language. Yes?
So it's generated after you emit source code and then you do some on the object?
Yes, well no, so the question is this happening after source code and then something on your object? No, this is before the object is generated. So this is where in the phase where GCC does all of the other data flow analysis, where it, before it does things like...
I'm just wondering if you can take it out and use it on any object.
Well, no, so it's a part of the GCC internals, so you can't use it on an object file that has been generated, although there is probably a way to do that if you then do the thing where you reconstruct a path from, just in a second, Jason, where you reconstruct a path from the object file, but this works with GCC internals. Jason?
You mentioned optimization flags. GCC in particular is good/bad at generating different warnings depending on optimization.
Correct.
Is there a
So the question is there a value in running the coverage at different optimization levels? For this, I would say yes. Simply because you're concerned with paths here, and especially the control flow graph will change drastically between optimization levels. The problem is that GCC recommends generally to run coverage on O0 because of that, and because mapping it back to the source code is just not possible at that point. But if we care about things like unreachable paths existing, or you want to see if there are relationships there that you think, but you actually want to verify with data, that's still very much a valid approach. But the guarantees just go down.
Okay, you're out of time.
I'm out of time, but I'll stick around for questions. Thank you very much.